Hello, everybody. My name is Alex Palcuie, and I'm a site reliability engineer at Google Cloud. I work on the team that takes care of the Google Compute Engine control plane, where you can create and run virtual machines on Google's infrastructure. I will be talking about the journey that our team has had, going from a handful of SLOs to millions of them, and how that improved the overall customer experience in the end. Now let's talk about what the control plane does. When a user sends an HTTP request to compute.googleapis.com to create a virtual machine, we first authenticate and authorize that user, verify that they have enough quota, check the status of their billing account, and then at the end, we return an ID for a long-running operation. Now, the user can poll that operation continuously and see its status. In the background, asynchronously, the backend code goes and grabs some cores and RAM for the VM from Borg, some disk space from our storage systems, talks to the networking folks to set up the virtual networking, maybe gets a public IP address for this VM, and that's mostly it. These backends actually have their own backends, and I've collectively labeled them as TI, which stands for the Technical Infrastructure Organization, where all the base services of which almost everything at Google is built on. Finally, we package the three parts, give the VM to the user by updating the status of the operation. And once we've returned the correct information, our job as a control plane is done. We're not responsible for keeping the VMs alive and running. We're not responsible for making sure the disks offer the right IOPS performance, nor that the networking doesn't drop a lot of packets. Those are the jobs of other teams running the GCP cloud and are part what they typically call the data plane. But GCE doesn't mean only virtual machine instances. We have many more resources. For example, VMs can be put into an instance group manager to treat them more like cattle. Disks are needed to store data for computation, and we can take snapshots of them. And out of these snapshots, we can create images that other VMs can boot from. We could attach an autoscaler to our instance group manager and scale up or down depending on how many customers we have. On the networking side, we have networks and subnetworks to partition. And every VM has an internal address, but they can rent a public IP address and attach it. For added security, anybody can establish firewall rules for the public resources, and we have forwarding rules for traffic outside of the network. All these resources and several others have all the create, read, update, and delete API methods you would expect for managing them. Not only that, but we need to provide these features across many locations. Our users expect that the control plane stack in a region in the US will fail independently from another region or independently from a region in Europe. Now, before delving more deeply into GCE, let's make sure we're on the right page with the three acronyms that I'll be using. A service level indicator, it's a carefully defined measure of some aspect of the level of the service. Typically, request latency is one of them, or another common one is error rate. An SLO is a target value for a service level that is measured by an SLI. For example, we might decide that we'll create VMs quickly by adopting our SLO that our 90th percentile latency should be less than 2 minutes. Finally, SLAs or service level agreements are an explicit or implicit contract with your users that include consequences when you meet or miss those SLOs. The consequences are easily recognized, typically financial, a rebate or a penalty, but they can be other forms. The last one typically involves lawyers, whereas the first two don't. So I'll focus on the first two. The GCE control plane SLOs are the textbook case for how to implement this concept. We define our availability SLI as the number of good requests divided by the number of total requests. A good request is a request which is not an internal error. For example, I'll claim that the availability SLO for creating an instance in the zone US Central 1A is 99.95%. This means that out of 10,000 requests, 5 are allowed to be bad, and the rest should be good. You see me throwing numbers of 9s in this presentation, but these don't exactly represent our internal targets. They're just representative of ideas that I'm trying to explain. Let's talk about latency and some tricks for it. An example of a typical latency SLO is that the 90th percentile for compute instances get should be equal or less than 10 seconds. Let's imagine that our system has received 9 requests with latency times going from 1 to 9. All our percentiles will match the latency. However, by default, your typical monitoring system stores latency entries in histogram buckets. Let's say that we have this exponential increase in bucket size, where the first one is size 1, second one is size 2, third one is size 4, and fourth one is size 8. When you'll ask your monitoring system what is the P90, it will give you a value between 7 and 15. It'll probably do some linear interpolation and might give a 9 here. But worse, if I change the duration of the last request, the histogram doesn't change at all. Now I'm violating my SLO, but the naive percentile would yield the wrong answer. The solution, in fact, is to turn latency SLOs into something similar with availability SLOs by counting how many slow and how many fast requests we have. The target latency now is similar with how we calculate the availability one. We define it as the number of fast requests divided by the number of total requests. A fast request is a request within 10-second target latency. Then we set the target to the actual percentile we're tracking, which in this case is the 90th. If I do the calculations for the latency where we had 1 request out of SLO, I get 8 good requests divided by 9 total requests, which gives me an 88% availability. Put there in quotes because we're actually talking about latency. This is lower than the 90% target, and it means we're out of SLO. On the right side, we're now 9 out of 9, giving us 100% availability, again in quotes, which is fine. This simpler way of tracking latency allows us to use less storage and simplifies the calculations. The major downside, though, is that we lose a lot of data about our distribution. But we don't really care about it when we compute latency SLOs. We can even aggregate multiple API methods under the same latency SLO. For example, in the top right corner, I've added a slower instances list API method, where the P90 should be 30 seconds, and an even slower instances insert, with the P90 being 60 seconds. On the left table, I've listed 10 requests, where 9 of them are fast, taking the rules from the table, and only one of them is slower. We're now measuring if the entire system is fast enough at the 90th percentile across many methods where we've separately defined targets. We're trying to find regressions as a whole and not only for a specific method. We now have all the necessary information to understand the initial definition of the GCE control plane SLOs. Back in the early 2010s, when we launched, we decided that we would have, for each zone and region, an availability, typical latency, and tail latency SLO. So for example, we would get paged when the zone US Central 1A had poor availability, or when Asia East 1C had degraded typical latency. The typical and tail latency just had different percentiles, tracking closer to the median or closer to the tail. There were no per API alerts, though we would typically catch when one API was broken by the virtue of setting our availability targets very high. This allowed us to have a manageable number of approximately 30 SLOs, and the strategy worked for a while. But turns out we have a Pareto principle distribution of requests, where 80% are reads and 20% are mutations. So when our QPS increased, tracking the health on a per scope basis actually meant we were tracking only read requests, which are not as high value as mutations. So when a high value low QPS method broke, we were alerted only when the burn was severe and long enough, prolonging the outage. So then we decided to add API method alerts in somewhere 2016. Now we would get paged when compute instances list had too many errors, or when compute disks list had a tail latency regression. Rather than the number of scopes times the number of API methods, we opted for the number of scopes plus the number of API methods. This took our number of SLOs somewhere into the hundreds, but it was still fine as we set tighter thresholds for higher QPS APIs and lower alerting thresholds for our low QPS methods. The strategy worked again for a while, but unfortunately, we grew again. Fast forward to 2022, we can see the increase in the scale of the GCE control plane. The problem now was that we were alerting only when a high QPS method broke in a zone, or when a high QPS zone broke a method. Small and medium zones and regions would not move the needle enough for our biggest API methods and would sometimes fall through the cracks. Even worse, we'd had outages where a newly launched region, which was small at the time, had a specific broken, very important API for a long period of time. And I would have my director come to me, and I would point to the green SLOs, and we all understood that it wasn't going to work out. These sort of things also did not go unnoticed, even in the outside world. Rachel Kroll, who writes on Rachel by the Bay, has a blog post where she describes a bad experience with one of the big platforms that, quoting, "They are huge. They are like a giant which lumbers around while you're a gnat. You're nothing to them." This becomes obvious when talking about some probleming experience at the hands of their system. The whole time their dashboard stayed green because from their point of view, they had tremendous reliability. We're talking 5 nines here, totally legit. Now, I'm not sure which platform she's talking about, but continuing in the same vein, meanwhile, you're having a bad day, nothing was working. Your business was in shambles, your customers were at your throat yelling for action, and all you could do is point to a vendor. What happened? Well, this is the point where we find out that their 5 nines availability is for their entire system. They see that and they're good. It's not a problem, everything is fine. You're the bug on the windscreen of the locomotive, the train has no idea you were there. And the orange website concurs. Million times this, it's shocking how elevated rate of errors for a specific endpoint in your cloud provider status page is actually amplified to be a soft outage of your product. I empathize with the feeling, and this is the problem my project has tried solving. While not perfectly, we have seen improvement. We started with getting a matrix of SLOs. You can see the dashboard here, where as rows we have API methods, and as columns we have the scopes. The squares there are SLO budgets over the last 30 days. A green square means OK. Red and black means we've exceeded our budget. Gray means we have an issue with a particular SLO that we know about. And we initially had 100,000 of these squares that we needed to take care of. I call this the beginning of our curse of dimensionality. But there's still a problem here. We're still very far away from the user. We can see which part of the GCE control plane is broken, but it's still abstract. You don't know which of the black squares or the red ones you should be focusing the most. However, let's simplify the previous matrix. On the y-axis, we again have the scopes. And on the x-axis, we have the API methods. That's a 2D view. We can actually improve it by adding another third dimension that represents our customers. If we, let's say, have 1 million of these customers that we care about, the number doesn't matter. It's the fact that it's orders of magnitude bigger than the previous 2 dimensions. This means that, in theory, we could have billions of SLO budgets, which could be like small rooms in this building. The real number, though, is closer to millions, because not all projects use all API methods in all scopes. The big number, which was close to 30 million when I started building the system, wasn't the main problem. It was the false positives when SLO budgets were blown. For example, when we say 99.95% reliability, we mean 10,000 requests allows us 5 errors. We scale that further and say 20,000 allows us 10 errors, and 40K allows us 20. If you go the other way around, though, we naively would say that 1,000 requests or less allows us only one error. So if it happens that a customer sent us 100 requests and we had one error, we would mark it as being out of SLO. That doesn't necessarily mean, though, they had a bad experience. They were just a bit unlucky due to the scale that we're working at. This skewed our data initially and made us appear worse than we actually were. To fix this, we could have said that 10,000 requests would be the threshold for being eligible for an SLO. But again, this provides a binary way of tracking reliability and would again satisfy only our biggest customers. So I came up with what I call the rule of 5 errors. For each SLO budget you've sent less than 10,000 requests, we need to have at least 5 errors for us to be alarmed. This gives us the beautiful logarithmic graph on the left side. You start with 50% reliability. If you've sent only 10 requests, you go pretty fast to 90% reliability if you've sent 50 requests. Hit 2 nines for 500 and 3 nines at 5,000. As you go infinitely to the right, the blue line will asymptotically stay at 99.95%. The rule can now be applied to our millions of SLO budgets, where we have few requests without giving us false positives. We can now start counting the real number of affected users. This is a time series of the number of out-of-SLO customers or projects in GCE parlance. We consider a project being out of SLO if it has at least one combination of API method and scope that's out of SLO. If we go back to the 3D building that represented our SLO budgets, every floor is a customer. Then if one floor has at least one room that's red, we count that project as being out of SLO. The red vertical lines represent when the GCE control plane had an outage. The green lines represent the end of the 30-day impact window for the said outage. You can pretty clearly see the spikes we had incidents on because the line goes down 30 days afterwards. The first part of the graph is pretty interesting because we've had 3 consecutive outages and then healing. In the middle, you can see that we had multiple outages happening in less than 30 days. The graph is inherently messy due to the fact that our production outages don't patiently wait for our SLO window to end before another one begins. We also have some kind of slow burn because the line never goes to 0. But we've managed to quantify it, point out the devs what to fix in which priority, and then impact most of our customers. One other thing to note is that the chart is logarithmic on the number of project axes. That's because one very big outage skews a lot of out-of-SLO projects. The way we've implemented generating the data is by running a data analytics pipeline over the logs. The pipeline starts daily, sometime after midnight. That's Mountain View at midnight for the folks familiar with how Google time zones work, and runs for 12 to 14 hours. We start every day with materializing the definition data. One definition is in the top right corner. We keep them as a protocol buffer in the code base, and each dev or SRE is empowered to change the definitions as they see fit. Materializing the definition daily from the code base to tables allows us to keep track of how our SLOs have evolved over time, and it also makes backfills easier if the pipeline has a problem. Then we have lots of SQL scripts that process the data in stages. For example, on the right-hand side, we have a 2-part SLI for the front end because we need to filter user requests with bad fields, such as zone USENIX or non-existent API methods. Another thing that helps us is to integrate the data with our ticket tracking system. Inside USO, we use a tool called Buganizer, known externally as Issue Tracker. However, most of the world has defaulted to Jira. We tag different scopes and API methods with tickets, and then they are surfaced in our dashboards. Inside Google, we use Dremel, an internal version of BigQuery, as the underlying tool for computing the data, but outside tools like Apache Spark, GCP's BigQuery, Amazon's Redshift, or other ones would be what I would recommend. I also recommend, again, keeping the definitions in a version control tracked system and doing code review when it changes, because this allows people to understand why and how you've arrived at a certain definition. On the real-time alerting side, we have much less granular data due to the cardinality of our alerts. However, we're working on a near real-time solution with a streaming pipeline, but it's early days for us. Here's a sample of the reports that we use in our organization. The first table shows a list of the worst SLOs for which we burnt the entire SLO budget, ordered by the number of out-of-SLO projects. We can see that compute region instances recommend location in the US Central 1 region is doing the worst. We've went more than 2 times the allowed error budget, and more than 500 projects have been affected by this. You can also observe that the next entry, the instances insert, has consumed 4 times the budget, with a significant amount of extra bad requests. However, it affects less products. Maybe it's inserts only for special GPUs that only fewer typical users use. Focusing on the first API method and fixing that would yield better results for more customers. The next table shows all the SLOs for which we haven't yet burned the budget overall. You can see by the fact that the ratio of SLO used column is below 1. However, we're still violating the reliability target for lots of our customers. Here, the first entry shows that instance group manager get HTTP method in aggregate has used only 21% of its budget. But for 289 customers, we've burned all of that budget. Typically, we would have missed these issues previously, but now they're surfaced, and they can be prioritized. Developers are able to self-serve themselves and pick up issues regardless of if we're in or out of SLO in aggregate. One extra thing is that for the first 2 tables, we have a drill down link. These open extra views showing burn down charts of the SLOs, samples of what the errors are, traces of very long requests, and anything that you need to understand fast what would entail a fix. The last table shows the most offending bugs we've identified, sorted also by the number of affected customers. We can see that get guest attributes is the worst one, and by following the link, you would see a discussion between dev and SRE about the current problems and what could be our next action items for fixing them. Thank you very much. This was my presentation.